In this presentation, we will focus on the shape measurement of specular objects behind frosted glass or diffuser plates. In the image, character C and B made of mirror are placed behind diffuser, but their shapes are completely invisible under ambient light conditions. However, by illuminating the diffuser with a laser pointer, light transmitted to the backside is reflected by the mirror surface, creating a pattern on the diffuser. We will perform the reconstruction of the three-dimensional scene from the image captured. This research holds broad potential applications. In terms of the method for reconstructing scene that cannot be directly observed, it bears similarities to non-line of sight imaging and can be viewed as one approach using a RGB camera. Leveraging specular reflection offers advantages as many surrounding objects exhibit specular reflection components, not only mirrors, but also ceramics and plastics. Furthermore, specular reflection components possess strong energy with less attenuation over distance compared to diffuser components, presenting another advantage. Our key idea is to use physically based rendering to correlate a 3D scene with its reflected light distribution. Rendering enables the reproduction of reflected light in complex scene, making it possible to estimate parameters for various scenes. As an approach to inverse rendering, optimization using differentiable rendering is employed to optimize the parameters of the 3D scene. There are two major challenges to realize this idea. The first challenge is the difficulty in rendering a scene where specular reflection light spreads across a diffuse surface. The second challenge involves the ambiguity problem, where there are many combinations of depths, normals, and reflectance for the same reflected light intensity. The first issue is that unidirectional algorithms which trace rays from the camera struggle with calculating light passes between diffuse surface and mirrors. Therefore, we propose an efficient bidirectional differentiable rendering algorithm that considers light passes from both the camera and the light source. The second issue arises from the inability of a single measurement to solve the ambiguity of reflected light. To address this issue, we perform observation with different light source positions. In our method, multiple measurements are conducted under different lighting. These measurements are input of physically based renderers to estimate 3D scene parameters such as depth, reflectance, and normals. First, we model the optical phenomena occurring in the scene. We assume specular reflection occurs only once. In a scenario where a diffuser is placed on a specular object, measurements are taken with a camera from above, as earlier stated in the diagram. Initially, the light from the light source reaches the diffuser, reflects off the object's surface, and reaches the diffuser again. Focusing on the tiny area of object surface indicated in the red, the light received by the infinitesimal surface area on the object is reflected and reaches the area on the diffuser. The energy must be conserved, so the energy on both surfaces must be the same. Therefore, the illuminance per unit area can be calculated as a reciprocal of the area. We employ bidirectional algorithms for rendering reflected light. During rendering, object shapes are represented by mesh. In the light source path, we generate a reflection light mesh that represents the reflected light distribution reaching the diffuser surface. Specifically, for each vertex of the object surface, we calculate the arrival position of the reflected light of the diffuser surface and compute the radiance of each phase based on its area. In the camera bus, we sample the reflected light mesh on the 2D image. One advantage of this rendering is the ease of connecting rays from the light source and the camera using mesh. To make this rendering differentiable, we use differentiable rasterizer for rasterization in the camera bus. This is a pipeline for parameter estimation using differentiable rendering. Scene parameters such as light sources, shapes, and reflectance properties are input into the renderer. The renderer generates RGB images, and the loss function is computed based on the difference between these outputs and the ground truth. During optimization, these losses are propagated, updating the scene parameters targeted for the optimization. The loss function considers reconstruction fidelity and the smoothness of the normal. Experimental results. The result of normal estimation. In this simulation experiment, the proposed method successfully estimates the normals, even if the object is concave or convex, or consists of straight lines or curves. This is a setup for the real-world experiment. You can see the reflected pattern is different for the light positions. Normal estimation results for real-world experiment. The results show the proposed method successfully reconstructs the object shapes, and phase directions are reasonably estimated. Also, it is possible to reconstruct the complex shape, which creates caustic pattern. Finally, we reconstruct flat mirrors having different shapes at different depths. In the simulation experiment, depth and reflectance distribution in the volume are successfully estimated from 9 observations. Results for real-world experiment. The proposed method is also successful to estimate depth and reflectance from 4 input images. In this presentation, we have shown that it is possible to analyze the reflected light distribution using differentiable rendering and to reconstruct a 3D scene. In the future work, we are planning to improve our model to handle reflection of more than 2 bounces. Thank you for listening.